Well, the study of large deviations is a big area in probability theory, but for me, I'm looking for combinatorial problems. So there's a little bit of a different emphasis than you might see in a probability course. But still, there are some similarities. So let me start with a pure probability theorem. So suppose that Sn is x1 plus xn, and xj is plus or minus 1 uniform. So just coin flips, the usual thing. You flip n coins, plus 1, minus 1, a random walk. And the theorem is that the probability that Sn is greater than a square root of n is less than e to the minus a squared over 2. Now, if a is fixed, we can say this is like the Gaussian, and so it's the central limit theorem. It's being a standard deviations off the mean. And if you look at the normal distribution, the tail is less than e to the minus a squared over 2. In fact, it's even a little bit better than that. But the strength here is, in this statement, there's no asymptotics. This holds for any n and any a. And I just write a squared of n because it's a nice parameterization. I could write probability that Sn is greater than b is less than or equal to e to the minus b squared over 2n. It would be the same thing. Okay. And I think let's put in here, but it doesn't matter. Okay, so this is really the first example of what are called the Chernoff bounds. The way we do it is we say the probability that Sn is greater than a squared of n is the probability that e to the lambda Sn is greater than or equal to e to the lambda a squared of n, which by Markov's inequality is less than or equal to the expected value of e to the lambda Sn e to the minus lambda a squared n. Now, so you might say we're taking the Laplace transform at lambda. The key thing is, which lambda do we take? We'll take the best lambda. We're gonna think of lambda as a parameter for a moment, and then we will optimize. This holds true for every lambda, but we're going to take the lambda that works best. Now, what is this expectation? How do we compute the Laplace transform? Well, it's very important that Sn is the sum of mutually independent random variables, because then this is the product is the product, and normally the expectation of the product is not the product of the expectations, but they're mutually independent, so it is. So this is the product over j of the expected value of e to the lambda xj. Of course, all the j's look the same, and this is, what is that? That's e to the lambda plus e to the minus lambda over 2 to the nth power. So actually this is the exact result, and but I'm going to just make an inequality that will be make it very convenient. So e to the lambda plus e to the minus lambda over 2, hyperbolic cosine of lambda, it begins 1 plus lambda squared over 2, and it's less than or equal to e to the lambda squared over 2. So this nice inequality. I put this once on the Putnam competition for American undergraduate students. Well, not exactly in this form, but the idea of you have hyperbolic cosine of lambda, you want it less than, the basic result was it's less than e to the lambda squared over 2. And one way, just look at the Taylor series. But the key thing is that the Taylor series start the same way. Hyperbolic cosine of lambda starts 1 plus lambda squared over 2, and then plus smaller terms. So an e to the lambda squared over 2 starts 1 plus lambda squared over 2. So that's why it's lambda squared over 2. And now you say that the probability coming from here is less than or equal to e to the lambda squared n over 2 minus lambda a root n. Okay, so that holds true for all lambda, and now we're going to optimize. We're going to pick the best lambda, so any high school student can, we don't even need calculus, it's just a parabola. And so what we do is we set lambda equal a over root n to make this as small as possible. And when lambda equals a over root n, we get a squared over 2 minus a squared, which is minus a squared over 2. Now, we did give up a little bit when we approximated the hyperbolic cosine of lambda by e to the lambda squared over 2. But if lambda is going to 0, that's a pretty good approximation. If lambda is not going to 0, we'd want to be more precise. And it turns out if you're dealing with situations where a is on the order of square root of n, then it turns out that this approximation of the hyperbolic cosine by the e to the lambda squared over 2 is not the one to take. And it's actually a nice exercise in calculus to keep it in this form and then to do the calculus, and it turns out you get the right answer. So, for example, the probability that Sn is greater than or equal to n over 10, you'll get, at least you'll get the log of the answer will be correct. The log of the answer will be correct. But those are, I think of those as very large deviations. I'm more interested, you can think of really 3 ranges here. When a is a constant, you want to use the central limit theorem. When a is on the order of root n, of course it can't be bigger than root n, tautologically. When a is on the order of root n, I think of that as very large deviations, and I'm not so interested in that either. So I'm interested in the case where a is going to infinity, so the probability is small, but a doesn't grow too quickly. It doesn't grow on the order of root n. And then this is actually quite a good bound, quite a good bound. Okay. So what is the idea of, these are called, I should say, Chernoff bounds. These are called Chernoff bounds, but especially since I'm in Russia, I should really say this is my fault. When I started working on this, I started calling them Chernoff bounds, and so everybody else started calling them Chernoff bounds, but there's a good argument that it goes back to Chebyshev or other people. But I mean, there was a paper by Chernoff that had something about. Anyway, that's ancient history now. So the idea of Chernoff bounds, you have a random variable z, and you want to bound the probability that z is greater than something. And you look at the expected value of e to the lambda z, and then you have the bound. So if you want the probability that z is greater than a, it's the probability that e to the lambda z is greater than e to the lambda a. So it's less than the expectation of e to the lambda z times e to the minus lambda a. But then the key thing is to optimize to pick the right lambda. Let's see how it works on the normal distribution itself. Of course, there we know the large deviation. It's given by an integral, but still, let's see how this method works. It actually is, it's particularly clean because the expected value, so now we have the probability that n is greater than or equal to a, is less than or equal to this, but the Laplace transform of the normal is particularly nice. The expected value of e to the lambda n is precisely e to the lambda squared over 2. Nice calculus exercise. And so this is less than or equal to e to the lambda squared over 2 minus lambda a. And then we see that the best result is to set lambda equals a. So, I mean, in the formal argument, in fact, sometimes when people write this out formally, they just say, set lambda equal a, dot, 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 dot. But I think pedagogically, I prefer to let lambda be a parameter, get the bound, and then use calculus to optimize. And the actual answer there's a nice calculus result that the actual answer is e to the minus a squared divided by root a. Okay, but the point is that this isn't bad. I mean, it's not that the Laplace, that the Chernoff bound gives the exact answer, but we're thinking of a large, and the actual answer is e to the minus a squared over root a. And we're getting a bound of e to the minus a squared over, e to the minus a squared over 2 over root a. And we're getting e to the minus a squared over 2. So the logarithm is asymptotically the same. And this is really pretty good for pretty much any application that I've dealt with. Let me take a simple place where you can use this. Suppose we look at I want to look at the random graph. Maybe I should define this because we're going to be talking a lot about this. The random graph has two parameters, n and p. So n is the number of vertices. And then between any two vertices, they are adjacent with probability p, and those events are mutually independent. So if you think you flip a coin for each pair to decide if they're adjacent, but it's not a fair coin. It comes up heads with probability p, and this is it. And so but in particular, when p equals a half, it is a fair coin. And if we look at the degree of a vertex, so a vertex has n minus 1 possible points it's adjacent to, And so this is has distribution binomial n minus 1/2, okay, which is, but we can put it in this form. Here we're adding plus 1s and minus 1s. Here we're adding pluses and 1s and 0s. So it's just a linear transformation. This is just s sub n minus 1 plus n minus 1 over 2. Just, and that's tautologically the same. And therefore, the probability that degree of v minus beta. So suppose we look at the degree. The expected value of the degree is n minus 1 over 2. What is the probability that it's off from n minus 1 over 2 by beta? That's just saying that s sub n minus 1, make sure I get it right. So we take the degree and we subtract n minus, so we get s sub n minus 1 over 2 is so that this is greater than 2 beta. Okay, which by this result here is less than e to the minus 2 beta squared over 2 n minus 1. I just reparameterize the beta. Now, so the scaling is that beta is on the order of root n, which is natural. The degree is a binomial, so it's like a Gaussian with, and so it scales like a Gaussian. But for many applications in graph theory, you want to say that all of the points behave in a certain way. This just comes up all the time. You'd like to say that that with high probability, all of the degrees are in a certain narrow range. So what we do we want this to be, yeah.
What's with the absolute value?
Oh, there's a factor of 2, sorry. It's symmetric, so it, yeah, sorry. You can put the absolute value, you just put a 2 here. Okay. So I'd like this to be little o of n to the minus 1, so now I just do some reverse engineering. And how big does beta have to be to make this n to the minus 1? Well, if beta is c root n root log n, the beta squared will be constant n log n. The n's will cancel. We'll get e to the minus log n. And if the constant, this isn't for any constant, for an appropriately large constant, which we can calculate, we'll get e to the minus constant log n, which will be little o of, we'll get little o of n to the minus 1. Okay. So what does that mean? That for that beta, what it says is that abbreviation, with high probability, all of the degrees differ from n minus 1 over 2 by less than constant root n root log n. So it's saying how concentrated the degrees are. So this is a typical place where it comes up. It also explains a lot of times there's a root log n factor that comes in. And there's a question, why do we have this root log n all the time? Well, the reason is that there's this Gaussian tail bound, which is e to the minus a squared over 2. So if a is root log n, the a squared over 2 is constant log n. I mean, you have to throw in the right constants. But if a is constant root log n, then a squared over 2 is constant log n, and e to the minus constant log n is polynomially small. Often we want the failure probability to be polynomially small. And to get it to be polynomially small, we often need to throw in an extra root log n factor because things are going like the e to the minus x squared over 2. Okay. So now, let me turn to a favorite problem of Erdős and certainly of myself. So I want to look at tournaments. So by a tournament T on n players, call the players 1 through n, I mean that each pair of players plays and somebody wins. But it's not necessarily transitive. That is, if I beats J and J beats K, it's perfectly possible that K beats I. So if you like, we could make it formally as a directed graph where for each I and J, either the pair IJ is a directed edge or the pair JI is a directed edge. Exactly one of those hold. But it's nice to think of it as a tournament, though the actual, we won't care about how the tournament is run. We just, and now, so this is a tournament. And then imagine that we have a ranking of the players. We call the players 1 through n. So sigma is a permutation on 1 through n. So if sigma of 7 equals 1, that means player 7 is ranked first. Sigma of 7 equals 11, that means that player is the 11th ranked player, etc. So we think of sigma as just a permutation. The players in the rankings are both 1 through n, so it's just a permutation. And now we define the fit. So far there's no probability. Everything's just a definition. We define the fit of the tournament to be the sum over each pair of players ij of xij, where x sub ij is minus 1 if it's an upset and plus 1 else. So what do I mean by that? We have a tournament and we have a ranking. So say we have two players, alpha and beta, and if you look at their rankings, alpha is ranked better than beta. So it's an upset if beta beats alpha. And it's a non-upset if alpha beats beta. So given the tournament and given the ranking, we can define the fit. Each game that's going the correct way, we count as plus 1. And each game that is going the incorrect way, we count as minus 1. And we just add them up. And now here was the question that Erdős started to look at and asked about. Yes?
Who's upset in this pair? First player or second one? I or J?
It's a good point. So you just take the pair. There's a ranking of the players. So you look at which player is ranked better. So it has the lower ranking because number 1 is the best. So it might be I or J. We don't know. That's why I wrote set IJ, not pair. So I take the pair of players I and J. I look at the player that has the lower ranking, the better ranking. If that player beats the other player, then it's +1. If he loses to the other player, then it's -1. But so it's just a pair of players. You could reverse it. It doesn't matter. You could say the same thing the other way. It's not the order. The two players are in order. It's whether the ranking and the game agree. If the ranking and the game agree, then it's +1. If the ranking and the game don't agree, it's -1. Okay? Yeah. So now, what Erdős then defined was the following min-max, which is given, think of it this way, given a tournament, you want to rank it as well as possible. So you want the fit to be as big as possible. Of course, there are other ways to rank, and this problem is about this way. So you take the ranking that gives the best fit. But then you say, what about the worst case? In the worst case tournament, how well can you rank the worst tournament? Which is, of course, now, if the tournament is transitive, you just use that ranking, and it's n choose 2. Now, just to say some simple things, sorry, I'm just too used to this notation. This is that CN2 that you write. Okay. So it can't be more than n choose 2 because that's the total number of games. But there's always a ranking where it's greater than or equal to 0 by the following simple argument. Here's the tournament. I tried this ranking. Oh, it gave a negative number. I reverse the ranking. And now I get the negative. Okay? Yeah. So if a ranking is negative, you just reverse it and you get positive. All right. And now, here is the first theorem. Which is due to Erdős and John Moon, who was from Alberta, I believe, maybe Calgary, I can't remember. Which is an upper bound on f of n. So, you know, it's interesting. We can turn max mins into a kind of logic because min is there exists and max is for all. And then it's really, this is saying that there exists a tournament such that for all rankings, the fit of the tournament to the ranking is less than or equal to this value. Okay, so let's see how they prove this. This was one of the early successes of the probabilistic method. But before proving this, let me notice that alpha is little o of n squared. Yeah.
Can you spell this? I can't see.
M-O-O-N. Moon. Like up in the sky. Here? Or this one?
No. The number. The estimate.
Oh, C, n to the 3 halves, square root log n. Okay. So the idea is we'll take a random T sub n. So our randomization is the tournament is random. That is to say, we have the n players, and each time a pair of players get together, and they just flip a coin and go out for a beer. You know, that's a random tournament, so we have a probability space. And now the claim is, for any sigma, so this is the thing to think about. Sigma is fixed, so you might as well think of it as 1 through n. It does, just think of the players ordered 1 through n. But the tournament is random. So what's happening is every game has probability a half of giving you +1 of being upset, non-upset, and probability a half of being an upset, because you just flip the coin. So it doesn't matter which player was ranked better, because they don't care. They're just flipping a coin. And furthermore, the coin flips are mutually independent. So what happens is that for any fixed sigma, the fit now has a random distribution, which is n choose 2 coin flips, you know, plus or minus on the coin flips. It's handy to do the coin flips with +1 or -1. It's just handy to do things with 0 expectation, but you do it the other. So therefore, the probability that the fit is greater than alpha, well, I erased it, but we had the bound. So it's less than or equal to e to the minus alpha squared over n times n minus 1. Because they're n choose 2, n times n minus 1 over 2 coin flips. So it was e to the minus alpha squared. Maybe I should, that in general, the probability that S sub m is greater than B see, I don't have to write it with the square root of m. This is the general result. So over here it's this, and now let so alpha is still a parameter. In the end, we'll solve for alpha. But let I sub sigma be 1 be the indicator that this is a good ranking, that is, the fit was bigger than alpha. And then let z be the summation of I sub sigma. And then the expected value of z, well, all the sigmas look the same. So there are n factorial possible permutations, and each one has probability e to the minus alpha squared over n times n minus 1 of having this. So now we really want large deviation, because what we want is that the probability of a good rank, so a good ranking is a failure for us. We don't want any good rankings. So the probability of a good ranking, because there are n factorial possible rankings, we want the probability of a good ranking, a particular ranking being good, to be less than 1 over n factorial. And this is the kind of extremely small probability that often comes up. So it's not just we want the probability less than 0.001. We want the probability less than 1 over n factorial. But we can just do a little bit of calculation. I mean, n factorial, we have Stirling's form. Actually, you could plug in n factorials less than n to the n. So from some analysis, you see that if alpha is constant n to the 3/2 root log n, this becomes n cubed log n. This is n squared. You get e to the minus n log n. So you get n to the minus c, which will cancel the n factorial for the right value of c. And so that was the proof of Erdős and Rainey. Sorry, Erdős and John Moon. It wasn't the best result. It wasn't the best result. Well, two things. First, this is just an upper bound, and I'll tell you about the lower bound in a minute. But even the upper bound wasn't the best result. The thing is that the sigmas, suppose you had two rankings that were pretty close to each other, then if one was bad, the other was likely to be bad. So sigmas that are close to each other are correlated in some way. And so that was the idea, that maybe this could be improved. And the actual theorem was first proved by me, but then de la Vega, Ferdinand de la Vega, gave the book proof. My proof was the anti-proof book proof. I mean, it was really, I've done a lot of ugly proofs in my day, but this one was, you definitely don't read this paper of mine. I mean, it was just tremendously ugly, which is that f of n is less than constant n to the 3/2, that is without the root log n factor. Yeah. I should say the c's are different in different theorems. C means it's a constant, but I'm not writing down the actual value. Okay. So this is an improvement of the upper bound by the root log n factor. And let me give you an idea of the proof. Here you have the n players in their ranked order. Okay, the one ranked first, second, third, fourth, fifth. Let's assume for convenience that n is a power of 2, but that's just a technical element. That's just a helpful technical element. We still have, we're going to take the random tournament, just like Erdős and Moon did, but the analysis is going to be stronger. So their analysis gave n to the 3/2 root log n. We're going to show that still for the random tournament, the fit is less than constant n to the 3/2, not constant to the n to the 3/2 root log n. Notice if there were only 10 to the n rankings, would be okay, because when you look at this bound, the root log n comes because n factorial is faster than exponential. It's like n to the n. So when you take its log and then its square root, you get an extra log n. So if the n factorial if there were only 10 to the n rankings, then we wouldn't have the root log n. And this is kind of the idea. We split the fit into actually a succession of values, but let me look at the first one. We have the ranking, and we look at we just look at the games between the first half of the players and the second half of the players. Okay? And just for each of those games, so we have the ranking, we have the top n over 2 players, and then the weaker n over 2 players, and we just look at those n squared over 4 players. So if we look at this, the same argument says, again, it's S, but now we're only looking at n squared over 4. Of course, it's just part of the argument. We have to do more after this. But now comes the key thing. How many for this problem, if we just want to look at fit 1, if we only want to look at fit 1, we don't really have n factorial rankings. Because really, all we're doing is splitting the players into 2 halves. Because for fit 1, I mean, for the whole problem, we do need the whole ranking. But for fit 1, we only need to know, so they're not n factorial different sigma. I mean, for this problem, they're only n choose n over 2 different sigma. So the effective because we're not really looking at the ranking. We're just looking at what is the set of the first n over 2 players and what is the set of the other n over 2 players, because that determines what you're looking at. We're not looking at the internal ranking in the top half or the bottom half. So now what we want is for this fit 1, we want the probability not to be less than 1 over n factorial, but less than 2 to the minus n. So what we get, we don't have a square root log n. We just have n to the 3 halves. Okay. Of course, we're not done. I mean, we want to solve the original problem. But this says if you have the random tournament and you're just saying split it into 2 divisions, two parts, 2 leagues, the top league and the bottom league. Now there are only 2 to the n ways of doing it, so you get this. Now then, oh, and then, of course, this, instead of this being n squared over 2, this is only n squared over 4, so that affects this constant. Okay, so you have to compute the constants. Now I'll just show you the second term of this. I now want to define fit 2 we look at the games between the first quartile and the second quartile, and also the games between the third quartile and the fourth quartile. And for each of them, we add +1 and -1. And now we say that this how many games are there? There's n over 4 times n over 4 plus n over 4 times n over 4. So there's n squared over 8 games. And now how many sigmas are there? Well, the number of sigmas, we're breaking n into 4 quartiles. So it's the number of ways to divide n into 4 equal sized things. So here, certainly it's less than or equal to 4 to the n, even if we don't worry that they're all equal. If you just split an n-element set into 4 parts. There are 4 to the n ways to do it. And so what we want is that the probability that s sub n squared over 8 is greater than or equal to c2 n to the 3 halves is less than or equal to 4 to the minus n. Okay. And again, we can compute the value of C2 that works. Furthermore, if we make it slightly bigger than C2, the probability will be extremely small that this occurs. Now what happens is the full proof, you divide it into halves, you divide it into quartiles, you divide it into octiles, if that's a word. You divide it into the 16 parts. So what you have is fit 1, fit 2, fit 3, fit 4. Each one gives you a constant, but what happens is the sum of the constants converges. And that takes some calculation, but basically what's happening, let's say we've split it into 1,024 parts, okay? Then, instead of this being n squared over 8, it's n squared over 2,048. We split it into 4, I think, something like that. And then, so what happens is when we apply this bound, this number here, this really helps us to make the C2 small because we're flipping a lot fewer coins. Anyway, one makes the calculation. I'm just giving an indication of the proof. And what happens is that the C's are rapidly decreasing, and indeed their sum is a finite sum. And so this was the very clever argument of Ferdinand de la Vega. Let me give a general result Suppose we have the sum of mutually independent random variables, and each one has mean 0. Well, that's just, we can always move to mean 0. And suppose that the variance of xi, let's just call it sigma I squared, and let's define sigma squared to be the variance of x, which is the sum of the sigma I squares. And let me say, so I'll just say often, so I won't write this as a theorem, often the probability that x is greater than or equal to a sigma is less than or equal to e to the minus a squared over 2 times some small term. So, all right, I mean, I'm not being totally precise here, and indeed, it doesn't always occur. But let me show you when it does occur and how you can check whether this is a case. So what we want to do, we want to set lambda equal a over n. Now, we do that with our fingers crossed because if x was Gaussian, we would want to pick lambda equals a over n. So we're just going to pick lambda equals a over n. And now we want to look at the expected value of e to the lambda xj. Well, let's do the Taylor series. It's 1 plus lambda times the expected value of xj, but it has 0 expectations, so that's 0. And then the next term is lambda squared over 2 times sigma j squared. And then there are other terms. So I'm going to write small. Sometimes it's big, but I'm going to write small here. And I'm just going to say, let's suppose that we're in a situation where this is negligible compared to this, and so we would get the first term would be 1 plus lambda squared over 2 sigma j squared, which would be like e to the lambda squared over 2 sigma j squared. If that's the case, this would imply that the expected value of e to the lambda x is the product of these, and now we're taking the product, so the exponents add, the lambda squared over 2 is a common term, and the sigma j squareds add up to sigma squared. So we would then get that this is e to the lambda squared over 2 sigma squared times 1 plus little o 1. And then the proof would end as before, the probability that x is greater than or equal to a sigma. So just like the probability that Sn was greater than or equal to a squared root of n, the sigma is like the square root of n, is less than or equal to the expected value of e to the lambda x, e to the minus lambda a sigma, which is the exponential of lambda squared over 2 sigma squared times the error term, which hopefully will be small, minus lambda a sigma, and I set lambda equal to we want it to be we want it to be Gaussian. We want lambda to be a over sigma. We want to think of x as being like a Gaussian mean 0 and standard deviation sigma. So we would pick lambda equal a over sigma. And when we pick lambda equal a over sigma, we get the sigmas all cancel out. We get a squared over 2 minus a squared, and we get e to the minus a squared over 2. It doesn't always work. But let me give you one case where it does work, which is nice. And in other cases, you have to make some calculations. The key thing is whether this number is close to this. That's the key. Whether the log of this number is close to lambda squared over 2 sigma j squared. If it's not, then you're in trouble. But if it is, so here's a case where it does work. Suppose that the xi's are less than or equal to k. And suppose, let me just get it right. And suppose that furthermore that A is little o of sigma. So in particular, lambda is going to 0. I could write this out with epsilons and deltas, but let me speak roughly here. Suppose you're in a situation where lambda is going to 0 and all of the xi's are bounded. Now what you do is you say that the expected value of e to the lambda, this is for all I, and the k has to be uniform. There's a uniform bound on the range. This is all I. So this is equal to 1 plus lambda squared over 2 sigma I squared plus small. And what we need is that the small is little o of lambda squared sigma I squared. So what we say is the following. So what is, we look at the full Taylor expansion. So we get for each u, we get expected value of xi to the u over u times lambda to the u over u factorial. So let's use the fact that for u greater than or equal to 3, the expected value of xi to the u, we can bound it in terms of the standard deviation because x doesn't get too big. So we just say that this is less than or equal to k to the u minus 2 times the expected value of xi squared, which is k to the u minus 2 sigma I squared. Well, that's not looking too good because k might be 20 and the powers are going up. But small is less than or equal to the summation over u equals 3 to infinity of lambda to the u over u factorial times the, it's actually the expected value of xi to the u, that would be exact, but let's bound it by the absolute value of xi to the u, and therefore we get, and let's take a lambda squared out, mainly because, and in fact, let's take a lambda squared out because that's what we want, and let's take the sigma I squared out because we want to compare it to this, and then we're left with lambda to the u minus 2 times k to the u minus 2. So it's summation from u equals 3 to infinity of k lambda to the u minus 2 over u factorial. Actually, it's just bounded by an exponential, but the key thing is, now it's important that lambda be going to 0. Otherwise, this is going to be a constant, and small won't be small. But if lambda is going to 0, then this is going to 0. And so we get that this is little o of this, and then we finish the proof as before. And one can actually make it more specific with epsilons and deltas. But so this idea is, I like to call this the Gaussian paradigm. You have some mutually independent random variables, make them all have mean 0, which is just a technical thing. When you add them, you have variance sigma squared. You'd like to say that the probability of being greater than a sigma is going like e to the minus a squared over 2. And using the Chernoff bounds, one can often do it. One has to be a little bit careful because it's not always true, but so try not to prove it when it's false, but it's in many cases it comes. So let me finish today Andre, I think about an hour is good. About an hour total is good. We didn't say the. I got one more. Good. So let me finish. Let me go back to the tournament ranking. And give a theorem that I showed, though this was the original, again, the original proof. It's now been proved many, many times. So this is not my proof. I'm not sure who came up with exactly this argument. Is that f of n is greater than constant n to the 3/2. So now things are going to be reversed. We're given a tournament, but we're not given a random tournament. An adversary gives us a tournament. So maybe it's the most possibly balanced tournament the adversary can come up with. But still, we want to rank it in such a way that there's some fit. And the particular amount of fit is going to be constant n to the 3. This constant and the other constant are different. I mean, we don't know the right constant in this problem, but we have the order of magnitude. That is, this says that since f of n is on the order of n to the 3/2. So here's how we do it. So now we have a fixed t sub n. But I emphasize again, it's not a random t sub n. It's an adversarial t sub n. Okay. And now I'm going to make a randomized algorithm to find the ranking. And there are a number of ways to do it, but here's a particular way I'm going to do it. I'm going to use what I like to call random greedy, sort of a generic term. Take the players and put them in random order. This is not the order we're going to do. This is part of the algorithm, okay? Take the players, but this is going to be a randomized algorithm. So I take the players and I put them in randomized order, and now I consider them, and now I'm going to create my ordering sigma, and here's how I do it. So I take the first player, there he is. Now I take the second player. If he beats the first player, I put him in front of the first player. If he loses to the first player, I put him behind the first player. Suppose I've ranked the first 9 players. I come to the 10th player. I compare him to the 9 other players. If he's won 5 or more of the games, I put him in front. If he's lost 5 or more, I put him in the back. I could do better by putting him in the middle, but let me just do it that way. So do we understand the randomized algorithm? The randomization is in the order, but after that, it's deterministic. You come to a player, you compare him to the previous players, and either he beats greater than or equal to half of them, or he doesn't. If he beats greater than or equal to half of them, you make him the first ranked player for the moment. You stick him in front, and otherwise you stick him in the back. So what's happening is sort of the ranking is spreading out, rather than, you don't know till the end who's the first ranked player. Okay. Where the above or below is deterministic. You just check the value of the games. Okay, now let's see how this does. For each player J, or maybe I should call him K, for each player K, but let me define x of a, b to equal plus 1 Let me just define that function. This is a deterministic function. The term that's been given to us. So I want to look at the sum of x of k a, where I guess I have it with the, I guess I have to say tau inverse of A is less than tau. That's a little bit annoying. That is, here's the ranking, and here's the player K. He's not in position K. He's somewhere in the ranking, and look at all the players that appeared before him, and for all those players, add up plus 1 or minus 1, depending on whether he beat them. Sorry, tau's the ranking, so tau inverse. The notation's a little bit bad, but this is what I mean. For each K, look at the players that came before him in this random order, and look at how he did against those players, and add it up, plus or minus 1. And now what I claim is that what this algorithm gives, without any probability, is that the fit, when you do this algorithm, is simply the sum of the absolute values of zk. Because you see, when player K comes up, maybe that sum was minus 20. But if the sum was minus 20, you put him at the bottom. So then he's so what's happening is you're plus 20 and you're scoring because you stuck him at the bottom. He was doing badly, so you put him on. On the other hand, if his score was plus 20, you put him on the top, you still get plus 20. So actually, let's say that again. You come to this player and you look at how he was with respect to the other players. If he was plus 20 against the other players, you put him in front of all the other players. So that means relative to those other players, you get a plus 20 score. But if he was minus 20, it would be the same thing because you'd stick him on the bottom, and then again you'd get a plus 20. Because again, you know, he's being put at the bottom, and he's minus 20 against them. And the total fit is you're adding for each player, you're adding how he does against the previous players, then you've counted each game exactly once. So this is an exact formula. The fit is exactly the sum of the absolute values of the ZT. Okay, in fact, with no probability. For any tau, you create the sigma by this method, and you calculate these Z sub k's, and the fit is given by this. But now what happens to a random tau? For a random tau, the expected value of the fit is the sum over k of the expected value of the zk's. And so fortunately I only have one prop, same one each time. So here we go. Here's our player. Okay. We need a volunteer. Thank you. Okay. Here's our player. And here are the players. Here are the 13 players he beats. So those are the plus ones. And here are the 13 players he loses to. So those are the minus ones. And please shuffle the cards well. It's not a hard job, but give it a good shuffle. A good shuffle. And let's see how we did. Remember, the ace of hearts means we stop. I think this is something in finance where there's some kind of futures where you can end at a random date or something. I always thought I could create a futures market out of this game, but okay. Which red was -1 or was it +1? I forget. I think it was -1. All right. Oh, this is +1. He beats. Red is +1 and black is -1. All right, so that's good. We're +1, +2. I don't know about this shuffle. +3, +4, +3, +2, +1. I'm getting less and less sure about this. 0, -1, -2. This is not a good simulation. -3. -2, -1, -2, -3, or which way are we going? -3, -3, -4. It's got to be. Hope you haven't hidden it. -5, -6, -5. Probably the last card. -4. -3, -2, I think it is the last card. -1, 0. Oh no. -1, +1, +1. That was not a very good random shuffle, I have to say. So there the value was +1, but if it had been -1, the value would be +1 too. And the calculation. Actually, we don't know how many games the player won, so we have to do it for because this is an adversarial thing. We have to do it for any number of. So here I did it with 13 red and 13 black, 13 +1s and 13 -1s, but it could have been 15 +1s and 11. So we have to do the analysis for all of them, but it turns out that there's some technical work. K is just any particular player. The expectation is on the order of square root of n. So just think of n as 1,000,000 now, and suppose it was really shuffled well, And now what we're doing is we're really doing like a Brownian excursion. We're really making a walk with +1s and -1s and +1s and -1s, except that our adversary has told us where we end up. So, but let's say we end up at 0, because it turns out that is the worst case. So what we're doing is we're taking a random walk of n +1s and -1s, where we're ending at 0. So, but actually we have n-1/2 +1s and n-1/2 +1s. And then there's a special card, the Joker. So what happens is you get this random walk, but then we stop it at a random point and we look at the absolute value. But, if you think of Brownian motion, the scaling is by root n. The scaling is by root n. So all of this can be done precisely, and one can show that this expected value is constant root n, and therefore the expectation of a sum is the sum of the expectations. Notice that's true even though it's very powerful. It doesn't matter that the variables are dependent on each other, and therefore the expected value of the fit is greater than or equal to constant n to the 3/2. So when we run this randomized algorithm, the expected value of what we get is going to be greater than or equal to constant n to the 3/2. And that means we can use Erdős magic. There is a realization of this algorithm that does give constant n to the 3/2. And so this really solved this problem, I mean, up to constants, which remain difficult. So just to go back over the history, the problem f of n is for the worst tournament. How well can you rank the worst tournament? And Erdős and Moon said you could keep the fit under constant n to the 3/2 root log n. I proved, but really the good proof was by Ferdinand de la Vega, that you could remove the root log n term to make it constant n to the 3/2. And then in the lower bound, I showed, and since then there have been many other proofs. My proof was not as nice as this, but there are many other basically randomized algorithms. So you're given an adversary gives you the tournament, but you run the randomized algorithm. Just to make an analogy here, it's a good analogy to quicksort. You know, so if you remember, the thing about quicksort is that, you know, if they're already sorted, it takes forever. You know, so quicksort works well, except it might take time n squared. And how do you handle that? Suppose an adversary, suppose one of your competitors is giving you the ordering, and you have to. How do you deal with an adversary giving you the data? That is the worst case. What you do is you do randomized quicksort. In the case of randomized quicksort, it's rather simple to explain. You just take the endpoints, and first you permute them randomly. So it doesn't matter what order they came in, they're now in random order. And then you apply deterministic quicksort, and then the expected time is n log n, which is, so this is a classic thing in the study of algorithms, at least when I teach it. I always tell it to the students. And things like that come up here as well. There's an adversary gives you an object, and then you want to find here a ranking, and somehow you make a appropriately chosen randomized algorithm, and you show that the expected value of the randomized algorithm is bounded from below, regardless of what the initial data was. So that's the idea. So just to tell you about the next two lectures, I think, so tomorrow will be percolation, so in all sorts of guises, but most particularly in the discrete. The basic thing will be the Erdős-Rényi model, GNP, but I'll talk about other models as well. That there's a critical point where the graph undergoes a macroscopic change. The physicists call it, you know, suddenly you're getting these giant components and things. So I'll talk about that Wednesday. Thursday we go to the parade, and then Friday I'll talk about the applications of this kind of probability to statements that you can make, what are called 0-1 laws, statements that you can make in a certain, what's called first order logic. Okay, I guess that's it for today.